Now, let's see the significance of the mathematical relation which we have obtained in the previous session. SP plus S dash P is equal to 2A. Now with this, the significance is that if I take the ellipse with the length of major axis being 2A and the foci being S as S dash which are fixed, then we can draw an ellipse using, we can construct an ellipse using this relation. So the significance of this is to construct an ellipse is what we are going to see in the session. So as can be seen, if I take two fixed points S and S dash nailed on this board, and then I tie a thread out here of length 2A, that is, I take a thread of length AA dash, and with this length of thread AA dash, I just tie it out to the focus. So I get the thread which definitely extends somewhere here. So I take a pencil or a pen and I put the thread fixed out here. So in this case, by holding tight, this gets straightened and this thread gets straightened, and I just draw fixed tight, I draw the line along the thread. So as I take the fixed end of the string, I do not make it loose, and then I draw, I get an ellipse. So an ellipse is obtained when I just take it and cut it. When I draw it with holding the string tight all the corners. So with this string out here, as I move, I get an exact shape of an ellipse out in case of using the relation SP plus S dash P equal to 2A, which helps us in constructing an ellipse in this manner. Constructing an ellipse using the fixed points S and S dash as nails and taking one of the point P as a pen or a pencil, I hold the string tight and just move it round so that I get an ellipse out here. Constructing an ellipse using the relation SP plus S dash P is equal to the length of major axis 2A. Auxiliary circle. Now, what is an auxiliary circle? Now that we have discussed about circle, now we're going to interestingly create a circle from an ellipse or describe a circle around the ellipse, which we call as auxiliary circle. So let's see how an auxiliary circle looks for an ellipse. Suppose I take the standard equation of ellipse x-axis and y-axis, then we know that the endpoints of the major axis are A and A dash. Now with these endpoints, I clearly can describe a circle with the diameter AA dash. Suppose using the diameter AA dash, that is using the length of major axis as the diameter, I just draw a circle or describe a circle along the ellipse. Is how I get a circle out here. Is how I get the circle. So with the diameter AA dash, the circle which I have described on this ellipse is called auxiliary circle. So this is the auxiliary circle along the ellipse, which is given by equation x square by a square plus y square by b square equal to 1, a greater than b. So for this ellipse, the circle is the auxiliary circle, and clearly we see that the auxiliary circle has the radius as a, because the coordinates of a are a0 and a dash is minus a0. Now radius is a and the circle has center as origin, therefore equation of auxiliary circle is given by x square plus y square equal to r square, with r being the radius a square. That's how we define the equation of auxiliary circle, with equation x square plus y square equal to radius square, that is a square. So auxiliary circle has center as origin and radius as half the length of major axis. So this has center as origin and radius is half of length of major axis, is how we describe the auxiliary circle and its features. Auxiliary circle along the ellipse looks like this, with the equation x square plus y square equal to a square. Eccentric angle. So let's see what is an eccentric angle. As we have discussed about the auxiliary circle being for the ellipse with diameter as a dash. Now this is the auxiliary circle for the ellipse in standard form. Now for here, the center is origin. Let me take a point P on the ellipse. So for this point P on the ellipse, let me drop a perpendicular on to the major axis. And let me extend this so that this cuts the auxiliary circle at some Q. So this line which extended cuts at Q to the auxiliary circle, we have I join C with Q. Then the angle ACQ, which is denoted by theta, is called the eccentric angle. It's very simple that this line which makes an angle in anti-clockwise direction is theta, which is called eccentric angle of point P on ellipse. So this is called ACQ, is called eccentric angle of the point P on the ellipse, x squared by a squared plus y squared by b squared equals 1, with a greater than b. Is how we define the eccentric angle of an ellipse, derived from its auxiliary circle. Angle ACQ is the eccentric angle of point P on the ellipse. Clearly we see that the eccentric angle varies accordingly as the point P moves throughout the ellipse in full 360 degrees rotation and comes back here. We have the point Q equally moving throughout this circle and coming back here. So as P moves, the Q also starts moving respectively, and hence the angle also changes. So the possibility is that the angle can move in all this whole rotation and come back till here is how we see the angle. Therefore, eccentric angle theta lies between 0 and theta, which is range of eccentric angle. So the range of eccentric angle is that theta lies between 0 and 2 pi. Suppose I take the ellipse in the standard form this with origin x and y axis. Now, if I take a point P on the ellipse and join this with angle theta, and let theta be the angle made by this point with center of the ellipse along x-axis. Now with this angle theta, we will define the parametric equations of ellipse. As we have discussed for a circle, the parametric equations were x equal to r cos theta and y equal to r sin theta for the circle x squared plus y squared equal to r squared. Similarly, the ellipse given by x squared by a squared plus y squared by b squared equal to 1 with a greater than b has the parametric equation representation, where I take P is equal to a cos theta and y coordinate as b sin theta, which clearly satisfies the whole of the equation of ellipse, where if I substitute x as a cos theta and y as b sin theta, I get this to be a cos theta by a square and b sin theta by b square, which when simplified as the left hand side simplifies to give a square cos square by a square plus b square sin square by b square, which gives cos square plus sin square, which after cancellation is nothing but sin square theta plus cos square theta, which is 1 using the trigonometric identity. But this is nothing but the right hand side. Therefore, x equal to a cos theta and y equal to b sin theta satisfy the equation of ellipse, making the left hand side equal to right hand side, which gives us the indication that these two are called the parametric equations of the ellipse. The parametric equations of ellipse are x equals a cos theta and y equals b sin theta, with 0 less than or equal to theta less than or equal to 2 pi. And theta is the angle made by the point on the ellipse with this in the anti-clockwise direction from the major axis, is how we identify in this case. So for example, I have another point P dash with this angle being alpha, then the parametric coordinates of P dash is not a cos alpha plus b sin alpha, because this is an anti-clockwise direction, and therefore I take in anti-clockwise direction this angle would be 360 minus alpha. If this is alpha, this would be the whole of 360 minus alpha is 2 pi minus alpha, Therefore, I get the coordinates as a cos 2 pi minus alpha and b sine 2 pi minus alpha, which on simplification gives the coordinates p dash connected with this angle. So every point has every angle for the ellipse through the center of the ellipse. Therefore, every coordinate represents, every parametric coordinate represents the parametric equation of the entire ellipse. Therefore, for each theta, x equal to a cos theta and y equal to b sin theta, with theta between 0 and 2 pi, are called the parametric equations of the ellipse in standard form. The next is the parametric point and its notation. So as we have seen that for the ellipse, x square by a square plus y square by b square equal to 1, with a greater than b, has the parametric equations as x equals a cos theta and y equals b sin theta. Then with this parametric equations, we define the parametric point. That is, the x coordinate always can be written in the angle form as p x coordinate, which is a cos theta, and y coordinate, which is b sin theta. So if I have an ellipse where the point P is making an angle theta with the major axis, this being center and this is a dash, then the parametric point is given by P of theta, which is P of a cos theta b sin theta. So instead of writing all the time the whole of x and y coordinates, this can be written as P of theta. So P of theta is assumed as P of a cos theta comma b sin theta. So the parametric point is P of theta, with theta lying between 0 and 2 pi. And theta is called the parameter for the parametric point P of theta. Is how we understand the parametric point. P of theta is the parametric point and theta is the parameter. So any point on ellipse can be represented by P of theta, the parametric point. Now generally, the equation of ellipse in standard form is denoted by S, which is x square by a square plus y square by b square minus 1 equal to 0. So standard form of equation of ellipse is denoted by S, given by this. And if suppose I want to find S11 for the point Px1 y1 referred with, then my S1 is xx1 by a square plus yy1 by b square equal to 0. And similarly, for the point x1 y1 referred with, I can find S11, which is nothing but x1 square by a square plus y1 square by b square, but this is a constant which is not equal to 0, or maybe. So if I have S2, I can write this as xx2 by a square plus yy2 by b square minus 1 equal to 0. And if it is S22, it is x2 square by a square plus y2 square by b square, is how we get the different types of notations. Say for example, I have 2 points Px1 y1 and Px2 y2. If suppose I have Px1 y1 and Qx2 y2, which refers to, then I can find S12 to be x1 x2 by a square plus y1 y2 by b square is how we identify the simplification of this, and this as various types of notations which we use for equation of ellipse and its respective properties. Now next comes the position of a point with respect to the ellipse. Now there are three cases where a point can lie in the plane where an ellipse exists. So let's see the three different cases of position of a point. Case 1, case 2 and case 3. So in case 1, I have an ellipse with P lying outside the ellipse. The point P lies outside the ellipse. Now I have case 2 where P lies inside the ellipse. And the third case is where P lies on the ellipse. So there are three cases of the position of the point. One is P outside the ellipse, P inside the ellipse, and P is on the ellipse. So with these three cases, we identify that for P which is outside the ellipse in case 1, we have the condition S11 which is greater than 0. So this is identified as the condition. So in order to identify the point to be whether outside or on or inside the ellipse, we simply need to find S11. So if S11 is positive or greater than 0, the point must lie outside the ellipse. And for inside, the condition is S11 is less than 0, and for case 3 where P is on this ellipse, we have S11 equal to 0 is the third case. So case 1, S11 greater than 0, case 2 less than 0, and case 3 is 0. So positive implies P is outside, negative implies P is inside, equal to 0 implies P is on the ellipse.